All right, folks, it's Bass Action back in action here. On this video, we're going to graph ellipses and hyperbolas, and as I work through this, I'm going to do a compare and contrast as we move down the page for what's the same and what's different between graphing the two. And what I want you to notice are those differences and similarities, and notice that there is a lot in common between the two. So let's just jump in. Let's look at the two equations that I've given you. So I've given you an equation here and an equation here. And the first thing that we want to do is we want to get in our head, what is it that we're graphing? And just like when we were looking at them in their non-standard form, of course you can see I've given these to you in standard form. You might have to work to get them in this form first. But now, just like when they're in non-standard form, what we're going to notice is that I have a plus here, and I have these two denominators that are different. And then on the next one, I have a minus. I don't even actually care about the two denominators at this point. So on the first one, with the plus and the two different denominators, that's going to be my ellipse. On the second one, that's automatically going to be my hyperbola. That's all I'm looking at. The next question we want to ask ourselves is, how can we determine what way it's been stretched or opened? So on the ellipse, what we're going to look for to determine what way it's been stretched is where the larger denominator is. So this larger denominator is under the y term, so it's under this y, and that's going to tell us that it's going to be vertical. It's truly that simple. On the hyperbola, remember we have an implied positive sign here in the front, and when we write the hyperbolas in standard form, we always lead with the positive. So what we're looking at for the hyperbola is we're looking really at this whole positive term, and since that term is regarding our x's, that's going to tell us that it's going to open in the horizontal direction. The next thing that we're going to do is we're going to find our center. And to find our center, we're going to look at the numerators, okay? The center is, of course, always going to be an xy pair. So when we go to look at those numerators, we're going to look at the x and then look at the y. So since there is no value being added or subtracted to this x coordinate, we can say that the x value for the center is going to be 0, and the y coordinate is 4, because what we're thinking in our brain is what value makes that quantity equal 0. When we come over here to the hyperbola, we look at our numerators again, and again we see a 0 and a 4. So far that's the same. Now from here, before we start to talk about vertices, we're actually going to start graphing. You'll eventually be able to do this mostly without graphing, but let's do a graph first to help you understand it. So for the center, for both of these, we're going to plot the point 0, 4. That part's going to be exactly the same. Then the values that are underneath each of the terms, each of those fractions, those values have been squared. Just like in a circle, the right-hand side of the equation is a radius squared. So instead of 9, we're going to think 3, and instead of 25, we're going to think 5. Since these values are the same on these two equations, I'm going to rewrite them over here on the hyperbola. Now, those values are going to tell us distances regarding that particular axis. So the 3, because it's under the x, tells me to move 3 from the center in each direction along the x-axis, okay, or horizontally is what we're really thinking. So 1, 2, 3, and I plot a point. 1, 2, 1, 2, 3, and I plot a point. Since the 3 is under the x in the hyperbola, I'm also going to go 3 in each direction. 1, 2, 3, and 1, 2, 3. And then I'm going to repeat that process with the y coordinates, okay? So I look at the y term, I look at the value under the y, I take the square root of it. Now, these won't always be pretty numbers, but just keep in mind, we're just taking the square root. Since the 5 is under the y, I'm going to go 5 up and down from the center. 1, 2, 3, 4, 5. And I'm going to do the same thing on the hyperbola because the hyperbola values were the same. So at this point, the two equations, oops, I just realized I counted that one too far. Sorry about that. Let's go ahead and fix that. There we go. Okay, so at this point, the two equations look exactly the same. Since our first one is an ellipse, from here we can actually draw in that ellipse. And just like when we talked about graphing circles, it might be helpful for you to actually turn the piece of paper and just do this a quarter at a time. It should not look like a football, okay? It does need to look like a smooth curve. For the hyperbola, what we're going to do is we're going to draw in this imaginary box. Now, this box is not actually part of the hyperbola. It's just going to help guide us. If you take this equation and you type it into Desmos, you will not ever see this box, okay? All right, so what we're going to do here is we've drawn in that box. It's just simply connecting each of the points we plotted. Each of those points should be a midpoint of the side of the box. The next thing we're going to do is we're going to draw in the diagonals of the box. And if you did your box correctly, the diagonals should pass perfectly through the center of the rectangle. So we're going to draw those in. Having a straight edge handy is always good. I'm kind of winging it here on the iPad. Okay. And then since we predetermined that because the x term was the positive term, it should open horizontally, we're going to sketch in our graph, and it should approach these diagonals because these diagonals are actually asymptotes. So it's going to come along that box and approach that asymptote. It should not curve back in. Okay, if you make yours curve back in, I'm going to ding you some points on it because it should be getting closer and closer to those asymptotes, okay? And you can always, of course, go back through and kind of smooth it out after you've roughed it in, okay? So that's the hyperbola and that's the ellipse in terms of graphing. Now, we're going to answer some other questions about it. To find the vertices in both cases have to be related to its direction. So because my ellipse is vertical, my vertices need to be in the vertical direction, which means that they're going to move from the center, and because this is vertical, that's the part of the center that's going to change when I write the vertices, which means I know that the x-coordinate of my vertices is going to stay the same. Now on my hyperbola, because my hyperbola is opening horizontally, it's going to be the x-coordinate that's going to change for the vertices, which means the y-coordinate is the one that's going to stay the same. So it's important to kind of get that in your mind, what part should be changing. Now the question is how much does that x-coordinate change by? Well, the vertices are these endpoints right here. So our vertices are right here and right here. Okay, oops, sorry, I meant to do those. Colored the wrong ones. I started off right. I was thinking about my hyperbola. So our vertices are going to be at the ends of this vertical. There's two of them. They're at the end of that vertical. If it was horizontal, we would have chosen those horizontal ones. And what we know is we got those points by adding and subtracting 5 from that y-coordinate of the center. So what I'm really thinking is a 4 plus a 5 and a 4 minus a 5. That's going to tell me that one of the vertices is at 9 and the other vertice is at a -1. And those do in fact match our graph. Okay, we're going to do the same thing for the hyperbola. This time we're going to look at what we were adding and subtracting to get to these points right here, okay, because it was opening horizontally. So in this case, we're adding and subtracting from that 0. So of course we can do this in our head. We're going to do a 0 plus a 3 and a 0 minus a 3, which gives us 3 and -3. The next thing that we're going to do is we're going to look at foci. Now, if you watch the video for the ellipse, you'll understand a little bit more what the foci are, but we have two equations that we just need to remember. And when you look at these two equations, you'll notice that they look like the Pythagorean theorem. Okay, they are connected to right triangles, but the proof of these is beyond the scope of our class. What I do want you to notice is that for the ellipse that has a plus between the two terms in the equation, we're actually using a minus in this equation. And for the hyperbola that has the minus, we're using a plus. So I just always remember it's backwards. Now, these C's, A's, and B's, these are those denominators of the equation from up above. So if I want to find the C value, I know the A and the B because they're the values that are underneath the terms in the equation. So for this problem, to find C, I would have C squared. Now, of course, when we're subtracting, the bigger one would have to come first. So it doesn't matter whether I call it A, but I just know I have to do 25 minus 9. So I have C squared equals 16, or in other words, my C value equals 4. That C value is going to be a distance from the center, and it's going to be along the same line that your vertices are oriented. So when we found our vertices, we kept the x-coordinate for this ellipse the same, and we changed the y. So now we're going to take a 4, and we're going to add a 4, and we're going to take the 4 from the center, and we're going to subtract a 4. That will tell us that our foci are at 8 and 0. And if you go back up and we plot those points, if we go back up here and we plot those 2 points, what we would find is that they are, in fact, these points that are just inside the ellipse. We're going to repeat that process for the hyperbola here. So again, we're going to have a C squared. At this time, we're adding, so it doesn't matter what order you do it. So I'm going to say 9 plus 25. So I'm going to get a C value of a square root of 34. So just like on the vertices, we're going to add and subtract from our x-coordinate this time. So I'm going to end up with a 0 plus a square root of 34 and a 0 minus a square root of 34, which of course I don't have to write the 0. So I have square root of 34, comma 4, and square root of 34, comma, negative, square root of 34, comma 4. Okay, the last thing that we're going to do is we're going to do the equations for the asymptotes. This is where knowing your point-slope form of a line is super helpful because we know that each of the asymptotes will pass through the center. So I can say y minus the y-coordinate of the center. I'm going to leave a gap here. And I'm going to say x minus the x-coordinate of the center. I'm going to go ahead and write the 0 for right now. So these values here are simply just the center. And then we need a rise over run. And of course, the rise over run is simply those distances that we moved from the center to graph those points. So let's come up here and look at the graph. I went up 5, that was the value, the square root of the value under the y's, and I went over a 3, so my slope is 5 over 3, and I have 2 of them. Now, sometimes you might have to clean up this equation or this slope, but that's all you're doing is you're reading those values from your equation up above. Okay, that's all I have. I know this was a long video, but when you get into these, you're going to find that these actually go really, really fast.